Hello, and welcome to the lecture on Chapter 13, titled The Birth of the Universe, which means we're going to be talking about how it all started, the Big Bang, how the universe was conceived, the birth of the universe. Okay, so we have this thing called the Big Bang Theory. It's a very widely accepted theory based on a huge body of evidence, but with some very compelling unanswered questions still left over. So, what were the conditions like in the early universe? So, what happened in those first few fractions of a second? And how did the early universe change with time? What was the evolution to get up to a point where galaxies started to be created? All right, so let's consider the conditions of the early universe. Okay, so one thing we want to think about is the temperature of the universe in those first elements of time. And to do that, we need to basically draw what is a very unusual graph. And it's a graph where the axis isn't linear, but is going in steps of 10. And then here we have time in those steps of 10. So the units are seconds, but notice the drastic difference here. At the very end, we have 10 to the 15 seconds. Okay? So that's leading up to the present day, which is 4 times 10 to the 17 seconds. That's a lot of zeros, right? 10 to the 17. And that, if converted into years, is about 13.8 billion years. So 13.8 billion years. But if we're going to stick with seconds, we need to then write it as this huge power of 10. The reason we would stick with seconds is notice what happens. If we go back, then we get down to very small amounts of time, down to when there was 1 second after the Big Bang, right? Because, of course, that's 60 seconds, all right? That's 1 second. 1 minute would be 60 seconds. You get the idea. But then notice that most of the graph are fractions of a second. 10 to the negative 5 seconds, 10 to the negative 15, negative 25, negative 35, negative 45 itself, which is the smallest element of time that is theorized to exist. Quantized time itself. So we're looking at tiny, tiny fractions of a second. Fractions of a second that are so much smaller than the most accurate measurement that we can make, which is probably on the order of nanoseconds or picoseconds, which would be 10 to the negative 12 seconds. No, this whole region from 10 to the negative 25 onward is such a small amount of time. But that's where most of the interesting things are theorized to happen based on our understanding of fundamental physics. Okay? So the trend is obviously going from a very initial high temperature down over this huge amount of time on this non-linear scale to the present day when the temperature has cooled to being on average in the range of 1 to 100 Kelvin. Okay? So quite a bit cooler. All right? Even here on the vertical axis, measured in temperatures in Kelvin, is logarithmic, which is to say powers of 10. Okay? All right. So that's the idea. The universe has cooled drastically, and we're mostly going to be talking about a very tiny fraction of time that happened at the very beginning. Okay? So one thing we want to consider is that in the very beginning of the universe, particles were being created from pure energy, and they were annihilating each other, creating more pure energy. Okay? Because the original universe, the conception of the Big Bang, would have been pure energy, no matter at all. But according to E equals mc squared, Einstein's famous special theory of relativity, we know that energy can become matter and vice versa. And so we had gamma ray photons, which are really high energy, very short wavelength photons of light, becoming pairs of electrons and anti-electrons, which are sometimes called positrons. Anti-electrons are called positrons. And the reason that you get a pair of particles from two gamma rays crashing together is because the charge must be conserved. So if you create a negatively charged particle, you have to create a positively charged particle as well, because the photons themselves had no charge. And so you must have a net zero charge to begin with, because you can't create charge out of nowhere. Okay? So there's these pairs of electrons and anti-electrons created by the collisions of high energy light. This can be recreated in the lab and is confirmed to be absolutely, totally possible. We can create matter from pure light in high energy conditions. But there was also a lot of particle annihilation. Because whenever an anti-electron and electron meet, they annihilate each other, completely converting their mass back into light energy, into radiant energy. Okay? So photons convert into particles, and antiparticle pairs, because the anti-electron is the antiparticle of an electron, and vice versa. The early universe was full of particles and radiation because of its high temperature. Okay? It didn't have any atoms to speak of. It just had the most fundamental particles, them and basically being created and annihilated again over and over again for those, well, few fractions of a second. Okay? Furthermore, there are 4 known forces in the universe. Everything we know about motion and dynamics is governed by these 4 forces: the weak force, the electromagnetic force, the strong force, and gravity. Okay? And we think that all 4 of those forces on the scale of 10 to the 32 Kelvin, which would correspond to the very, very, very beginning of the universe, essentially the first moment of the Big Bang at 10 to the negative 43 seconds, that at some point all 4 of the forces were one, a superforce, a grand unified theory. But gravity was the first force to split off. It's the most different of the 4 fundamental forces. Then there was thought to be a short period on the order of 10 to the negative 43 to 10 to the negative 38 seconds as the universe cooled, right, in that tiny, tiny fraction of a second, where the 3 remaining forces formed the gut force, which stands for the Grand Unified Theory Force. Okay? And this one here, super force, would be kind of the theory of everything as opposed to the Grand Unified Theory, although I didn't mention that. Okay? And then the next to break off is thought to be the strong force. And we'll come back to the significance of the strong force becoming an independent force from the rest. Following was a period for a month, for longer, right? Up to 10 to the negative 10 seconds as the universe cooled significantly, where we had the electroweak force, which is a combination of the electromagnetic force and the weak force acting together as one. And the electroweak force can actually be recreated in the most powerful particle colliders. So we can confirm that the electroweak force, we can see its behavior, we can see systems that can only be explained by the electroweak force. And if you're wondering what the weak force is, the weak force is the force essentially that creates what's called one type of radioactive decay called beta decay. It's sort of the force that has to do with holding a neutron together. On the other hand, the strong force is the force that holds the nucleus together. It's the force that keeps protons from tearing apart the nucleus. Okay? And of course, the electromagnetic force is the force that, that drives electricity. So which of the 4 forces keeps you from sinking to the center of the Earth? It's a trick question, because I bet you have one idea in mind, but then you might be questioning it because you're like, well, what keeps me from sinking? What's actually stopping you from sinking into the ground? What makes the ground solid, so to speak? Well, it's actually electromagnetism. Because what makes matter solid, what holds molecules together, is the electromagnetic force. All solids, all molecules are made possible by electromagnetism, unequivocally. Now, you could argue that it's the strong force because you can't have atoms to make molecules if you don't have a nucleus. But on a more immediate level, it's electromagnetism that makes solids solid. So, do forces unify at high temperatures? Well, we certainly think so. So the 4 known forces in the universe, the strong force, the electromagnetism, the weak force, and gravity, are known to work, right? The electroweak force definitely can be confirmed to be a phenomenon at high enough temperature. We see its behavior. And so we can extrapolate that and theorize that all the forces at the high enough temperature can fuse together. Okay? So how did the early universe change with time? What are the key periods in those first tiny, tiny fractions of a second? Okay, well, we're going to go through and discuss each of them. And I think this is rather interesting because we get to kind of take a visit on each moment of the early Big Bang and think about how it set the groundwork, how it established the rules of the universe and the players in the universe in terms of the particles that exist that we have today. So in the very first moment, the 10 to the negative 43, when perhaps gravity was unified with the other 3 forces, that's when we had the Planck era. And it's called the Planck era because that's the time of 10 to the negative 43 to 10 to the negative 45 is Planck time. It's, as I said before, it's the quantization of time. It's the smallest chunk of time that's theorized to exist. But we can't come nowhere near to experimentally confirming that yet, or maybe in the near future, but that's the idea, okay? And we really don't know we have no way of establishing a theory for that. There's no real valid theory of quantum gravity. Following, however, is the gut era, which is the Grand Unified Theory era. And this lasts from Planck time to the end of the gut force at 10 to the negative 38 seconds. Okay? Following is the electroweak era, which lasts from the end of the gut force at 10 to the negative 38 seconds to the end of the electroweak force at 10 to the negative 10 seconds. Next is the particle era. All right, so now we're getting into really when might seeing things that are more familiar to what the world looks like today, or the universe looks like today. Amounts of matter and antimatter nearly equal, roughly one extra proton for every 10 to the 9 proton-antiproton pairs. Okay, so for whatever reason, there is the ability for more protons to last in the early universe, and thus all the antiprotons got annihilated. And there was also more electrons than anti-electrons, and so all the anti-electrons got annihilated, and we're left with matter as opposed to antimatter. But it was a careful balancing act, because you think that the matter is created from pure energy, and it's always created in pairs, but so there was a slight just statistical likelihood of certain ones to survive more. And once their population became larger, once you had significantly more electrons and protons than their corresponding antiparticles, then that's what the universe was going to be established as. Because fundamentally, antiparticles can't survive very long. They're created, again, in particle accelerators and other high-energy physics experiments here on Earth, but every time they interact with an electron, there's a lot of electrons out there just swirling around at the microscopic scale, at the submicroscopic scale. Well, when an anti-electron runs into an electron, they annihilate each other. So the point being, they don't last very long. Antimatter is fundamentally unstable. It can be trapped in magnetic fields and kept away from ordinary matter if it's very carefully collected and directed into those magnetic fields. And so it's thought of as being the most expensive substance on Earth. Kind of like actually getting a significant amount of antimatter in one place. But it's dangerous because if you have too much antimatter in one place, and if you suddenly released it, then it'll just come in contact with ordinary matter and then release a huge amount of energy in the annihilation. It'll be the most powerful explosion ever. Okay? But anyway, we have ordinary matter instead of antimatter that exist here in the universe. And then we go into the era of nucleosynthesis. This begins when matter annihilates remaining antimatter at about, look, we're not so small now, 1 millisecond, so a thousandth of a second. And this is where the nuclei also begin to fuse. Okay, so you actually start getting protons fusing together to make nuclei. Now, not really many nuclei. You basically are just going to get nuclei that have one proton, so that's the nucleus of a hydrogen atom, and other ones that have 2 protons and 2 neutrons, which is the nucleus of a helium atom. There's no other elements that are thought to exist. There's some debate on whether a few trace amounts of heavier elements could have been created in this early era of nucleosynthesis, but it's thought that only hydrogen and helium were created, which means all the heavier elements, everything else on the periodic table, from nitrogen to oxygen, neon, all the way up to gold and uranium, were all created later inside of stars and other, star remnant collisions, like neutron star collisions. And we go into the era of nuclei. This is where the helium nuclei form at about 3 minutes. Okay, so we have already hydrogen atoms being established, or hydrogen nuclei being established, and now also helium nuclei. Notice we're saying nuclei, not atoms. There's a reason for that. The universe became too cool to blast helium apart. Okay, so that's why it was stable. Okay, and now we have actual atoms, because now the universe is cool enough for that basically what was entirely ionized hydrogen and helium to become neutral hydrogen and helium. And the difference between an ionized atom, which is just the nucleus stripped of all its electrons, and a neutral atom is that a neutral atom has its electrons. But in a very high energy state, where there's so much energy around and all the particles are bouncing into each other, because that's really what temperature means, is like very high kinetic energy per particle. Fundamentally, that is what it means. Then all those atoms are going to be losing their electrons because there's too much energy to hold on to them. They get bounced away, stripped away. So that's an ionized gas. And another term for an ionized gas, a gas where all the electrons are stripped from all of the nuclei, is a plasma. So up until the era of the atoms, the universe was entirely a plasma. But now we actually have stable atoms that can exist because the universe has cooled. But notice the difference in time. We went from the first few seconds finally onto a few minutes, but the era of nuclei lasted for 380,000 years. All right? So we have this point then, right, where it took a long time until the first atoms could form. It took a long time for that plasma to cool enough to actually start becoming an atomic gas. Okay? And at this point, when finally the plasma that was the entire universe actually started to become an atomic gas, that's when the background radiation was released. And what I mean by that is up to this point, there was still a bunch of photons, right? We talked about photons becoming matter, but there's plenty of photons that never became matter. Plenty of light, radiant energy that just remained radiant energy, just remained light. Well, that light was trapped because the plasma is so dense and it's so energetic that every time a photon tries to travel somewhere, it just bumps into something and gets ricocheted. Okay? Because photons, although they don't have mass, they have momentum and they get bounced off of matter. And so then what's happening is you have a bunch of trapped light energy. But once the universe is cooled enough that the electrons can safely bond to the positive nucleus, well, now the photons are actually able to with more likelihood, leave the gas. All right, they actually have a chance of radiating outwards, and that means there is a net signal of traveling photons, traveling light that is now leaving the early universe. Which means, with a powerful enough telescope, we can look back and see that original signal, and that's called the background radiation. It's the oldest signal that exists in the universe. It's the signal from 380,000 years after the Big Bang. The first time there's any signal, because until then, all light was trapped, thus all information was trapped, and there is no signal from that earlier universe. Then we enter the era of galaxies, which starts at about 1 billion years, although there are some galaxies that we now think started as early as 300 million years, but somewhere between about 300 million years and a billion years, the first galaxies started to form. Perhaps they started forming as much smaller galaxies like globular clusters that we see today, but whatever was that early process of galaxy formation, it started after a few hundred million years and really kicked up at 1 billion years. And then we continue on to today, we're at 13.8, almost 14 billion years. Okay, so that's the picture, but obviously we're really focusing on these incredible phenomena that happened early on. All right, so what have we learned? We've learned that the early universe was so hot and so dense that radiation was constantly producing particle-antiparticle pairs and vice versa. And how did the early universe change with time? Well, as the universe cooled, particle production stopped, leaving matter instead of antimatter, right? So we ended up with a universe made out of matter. To be fair, if we ended up with a universe made out of antimatter, we'd call it matter, right? Then we had fusion, turned remaining neutrons into helium, okay? So that's how we ended up with helium nuclei. Then the radiation traveled freely after the formation of atoms, once the nuclei began to be able to actually bond with electrons. Okay, now, let's talk about how we can actually support something like this, because this just sounds like fantasy so far, right? But there is some really compelling evidence to support the Big Bang. Our questions are, how do observations of the cosmic microwave background support the Big Bang theory? And how do the abundances of elements support the Big Bang theory? Okay, so 1. We've detected the leftover radiation from the Big Bang. At that point, 380,000 years after the Big Bang, when the first signals were released from what was a plasma is now an atomic gas, we actually have picked up that signal. Okay, the pair of scientists that actually first found it, they weren't looking for it, they stumbled across it, got a Nobel Prize for this amazing, kind of perspective-changing discovery. The Big Bang theory correctly predicts the abundance of helium and other light elements. So if we look at how much helium and hydrogen there is, and it absolutely matches our understanding of the model of the Big Bang. Okay, so how do observations of the cosmic microwave background support the Big Bang theory? Okay, so the cosmic microwave background, the radiation left over from the Big Bang was detected by Penzias and Wilson in 1965. And this was the radio telescope that they used to do it. Okay? So the background radiation from the Big Bang has been freely streaming across the universe since atoms formed at a temperature of about 3,000 Kelvin. Okay? So to give you the idea about 3,000 Kelvin, that's like something that's kind of glowing red hot, but on the low end of red hot, so it's somewhere between right at the border of visible and infrared. It's the surface temperature of smaller stars than our own sun. Our own sun has a surface temperature of 5,600 Kelvin. So it's a hot temperature, but it's not unbelievably hot. So obviously this was a universe that had cooled significantly from when it was almost like so hot that it's hard to perceive. Furthermore, it doesn't correspond to microwaves, right? Because you think, well, if you think about the idea of light and how light is related to temperature, we've talked about this significantly, and the name for that relationship is called Wien's law. How if you know the color of something, then you know its temperature, as long as that something is a black body, which is a solid, a solid that's radiating energy. It doesn't apply to a gas or an ionized gas, but it definitely applies to any solid, including stars. Now, the thing is that the reason that we'd have light that was initially visible, but now is a microwave, is because of the redshift. Now, we've talked about the redshift, right? We talked about the redshift when we talked about Hubble's law. That idea that the further a galaxy is away from us, the faster it's moving away from us, thus the larger its redshift. All the characteristic emission lines of known elements are shifted towards the red. In other words, all the wavelengths are longer than they would be in a laboratory measured on Earth. Same idea here, but it's the most dramatic redshift that exists because it's the oldest signal in the universe. So we have something that originally started off on the order of about 700 nanometers, but has gotten so long, okay, so it went from 700 nanometers to a fraction of a centimeter, right? So we can see here that now the wavelength is about 1.1 millimeters long. That's a huge redshift to go from 700 nanometers, so that's 7 times 10 to the negative 5 meters, all the way to 1.1 times 10 to the negative 3 meters. So we had a redshift from this original signal, which was quite short, to a much, much longer wave. Because in the time that initial cosmic microwave background radiation was produced, the universe is stretched out so much that the light itself has stretched with the universe. It's called cosmological redshift because it's a bit different to understand. It's the same consequence, same math. It's the same idea, but it's instead of understanding that the remnant of the Big Bang is moving away from us so fast that it's thus there's a huge Doppler effect. Instead, we can say that the photons have stretched in the time since they were created, because photons are part of the universe. So if the universe stretches and expands, so too must the photons. Okay? So now the background radiation corresponds to a temperature of 2.73 Kelvin. But of course we know it wasn't created at 2.73, it was created at 3000. But that's wonderful because that allows us to calculate how far away it is. Okay? All right, so the expansion of the universe has redshifted the thermal radiation from that time to 1,000 times longer wavelength. See, 10 to the negative 3 to 10 to the negative 5. Okay, so 3 orders of magnitude. Okay, over 2 because it would be 2, but then we got 7 to 1, which almost gives us another order of magnitude. Okay, so Planck gives us detailed baby pictures of structures in the universe. All right. So how do the abundances of elements support the Big Bang Theory? Well, let's think about what was happening with matter early in the universe. So protons and neutrons fuse to form a deuterium nucleus. 2 deuterium nuclei fuse to make a hydrogen-3 nucleus. Hydrogen-3 fuses with deuterium to create helium-4. So deuterium, by the way, is an isotope of hydrogen. It's just hydrogen with a neutron, because normal hydrogen is just a proton. And then hydrogen-3 is an isotope of hydrogen where it's missing one neutron. Now technically everything is an isotope, but the most abundant form of helium is helium-4, where there's an equal number of protons and neutrons. In other words, there's 2 protons and 2 neutrons. And so then we can see that's the final process, the final product of this process, is we get helium-4. Okay? So protons and neutrons combine to make long-lasting helium nuclei when the universe was about 3 minutes old, and the helium-4 is the long-lasting kind. Okay? And so the Big Bang theory predicts that the universe should be 75% hydrogen and 25% helium by mass. This prediction matches observations of primordial gases. So when you look at the earliest protogalactic gases, we consistently see this ratio of hydrogen to helium. So which of these abundance patterns is an unrealistic chemical composition for a star? Based on the fact that the universe started with 75% hydrogen and 25% helium. Think carefully about it. It's a really good one to make sure you can kind of understand a simple consequence of these ideas. Okay? You see it? It's 95% hydrogen. Because there's no way for a star to have that much hydrogen. We say that stars are mostly hydrogen, that's true, but they could never be 95% hydrogen because the universe itself isn't 95% hydrogen. It'd be incredibly unlikely, almost impossibly unlikely for a star to have that much hydrogen. All right, so what have we learned? How do observations of the cosmic microwave background support the Big Bang theory? Well, the radiation left over from the Big Bang is now in the form of microwaves, the cosmic microwave background, which we can observe with a radio telescope. Okay? And and the redshift matches the age that is consistent with Hubble's law. Okay? So that's a big one. How do the abundances of elements support the Big Bang theory? Well, the observations of helium and other light elements agree with the predictions for fusion in the Big Bang theory. Okay? So now let's talk about the most troubling part of the Big Bang theory, because it requires something called inflation. Okay, so what key features of the universe are explained by inflation, and did inflation really occur? Okay, so inflation is such a conundrum. And one way to maybe motivate the idea of inflation is to go back to something we just talked about, which is the cosmic microwave background radiation. Because you might think that if this is the earliest signal that was ever created, and these scientists discovered it with a radio telescope, then they must have found it by looking at one part of the sky, right? They must have looked in the direction of the Big Bang and found that remnant, that signal. And maybe, that signal was spread across a big chunk of the sky because it's been spreading as the universe is expanding over the last 14 billion years, almost 14 billion years. So that would make sense, right? But here's the thing. When they look at the cosmic microwave background radiation, they find it in all directions. If this represents the celestial sphere, and this is the north of the celestial sphere, I'll draw it up here so you can see it. Here's the south and the east and the west of the celestial sphere, basically looking from it, up into the sky from any direction on the planet, and then kind of mapping out the sky. That's the idea of the celestial sphere. Then we see the cosmic microwave background radiation shown here as this red, pattern everywhere. And we see some variation in the microwave background radiation, but we see no significant trend. There's no part where it's obviously more powerful than others. We just see an overall random variation in the radiation, but it completely covers the sky. So that means that no matter where we look, we see the Big Bang. Well, how is that possible? Because the Big Bang had to be a point source. So how do you go from a universe where you look in all directions and everything looks the same? Because furthermore, if we look back, we can see galaxies that are 10 billion years old in every direction. It's not like we look in one direction and we only see the young galaxies because we're looking towards sort of the expanding crest of the universe. And then we look in another direction and we see, the older ones. That's not the case. We see old galaxies in every direction. Again, no variation. That's incredibly troubling because on the surface it seems like it just contradicts the Big Bang, because we couldn't have had a single source if everything's the same in the same directions. It seems like the universe must be static, right? It has to be. But it's not. It really is not, because otherwise you wouldn't have Hubble's law. There's a significant trend, and there's a trend towards everything approaching a single point, and then the cosmic microwave background radiation completely is consistent with Hubble's law. So what's going on? Well, one way to reconcile it is to talk about inflation, okay? So mysteries that need explanation. Where does the structure come from in the universe, okay? Both in the microwave background radiation and in just the distribution of galaxies, young and old. Why is the overall distribution of matter so uniform? And why is the density of the universe so close to the critical density? All right? Well, an early episode of Rapid Inflation can solve all these mysteries. Okay? So inflation can make all the structure by stretching tiny quantum ripples to enormous size. These ripples in density then become the seeds for all structures in the universe, eventually creating galaxies. Okay? And it allows for this idea, right, or maybe it answers this question, of how can microwave temperatures be nearly identical on opposite sides of the sky, right? Because they're too far away to have communicated with each other. Because they're both signals from, like as I said, from 380,000 years after the Big Bang. They're the first signals that were ever created. But if we look at opposite directions, and they're opposite sides of the universe, there's no way they could have communicated with each other. So there can't be some behavior that's like spreading the effect. It can't be like a ripple effect of the signal spreading out, because we're looking at clouds that have never been able to communicate because they are traveling away from each other at relative speeds faster than the speed of light. Not an absolute speed faster than the speed of light, but relative speeds faster than the speed of light. Information from one, section of the signal that is cosmic microwave background radiation could never have communicated with the other. A could never have communicated with B. So they must have a common origin. All right? They must have come from a common point. And that common point must have been the point source, origin of the universe itself, the Big Bang. But if that's the case, then there must have been some period from 10 to the negative 38 to 10 to the negative 36 seconds, based on models that are beyond the perspective of this class. But there must have been, in that early period, a rapid inflation of the universe, where the universe went from being on the size of, just a single point at first, and then maybe just on the size of a galaxy, if that, to being almost as big as it is today. So that's the only way we can explain the uniformity of the microwave background radiation and galaxies themselves. Okay? So that's an incredibly difficult idea, though, because it requires, I'm going to go back to it, it requires us to accept that the universe expanded so much in such a small amount of time. And if that's the case, if this distance became so big in such a tiny fraction of a second, that means that the universe would have had to have been expanding, faster than the speed of light. And that's one of those golden rules that you never break. But inflation breaks the speed of light. Absolutely. Now, maybe it's allowed to break the speed of light because it was this space-time continuum itself that was expanding at such a fast rate, but it's still an incredible difficult thing to accept. And we have no physics that actually suggest how it could have worked. We just can say that it had to have happened because there's no other explanation. Like I said, troubling. Okay? Now, talking about the space-time continuum, when we think about how much matter there is in space and how that matter is spread out, we talk about density, because density is just mass in kilograms per volume in cubic meters. And it turns out there's a certain amount of density in the universe that suggests that it matches the critical density, which means that space-time has a general behavior of being flat. Now, there's going to be divots in space-time where you have a large concentration of matter, like a neutron star or especially a black hole. So you have little dips and divots throughout the space-time continuum, but the overall structure is flat. There's no general trend to it. And that's important because that means if you send signals out that are parallel to each other, imagine shooting two lasers, for example, right, light, well, those signals will remain parallel forever. And that's different than a universe that has density that's greater than the critical density, because in such a universe, space-time itself would be curved back over. So if you shot parallel rays, they would meet. Okay? And the other hand is you would have a density that's less than the critical density, in which case you have a saddle-shaped space-time continuum. In that case, parallel rays diverge in different directions. Okay? And instead of remaining parallel. All right? They won't meet, but they don't remain parallel either. And so these other types of universes, these other types of space-time continuum, they're plausible. That certainly could be the universe we lived in. And for many decades, we thought we lived in a universe that had a density greater than the critical density. And the Big Bang was maybe part of a cyclical process where the universe would expand and then slow down its expansion and then eventually contract again. But now all of our measurements show that that's not the case. And we'll talk about that in the next chapter when we talk about dark energy. But even without talking about dark energy, we can acknowledge that we live in a universe with a flat space-time continuum. And I do want to clarify that I'm not talking about flat space. I'm not saying that all the galaxies and all the clouds between the galaxies, that they're on like a plane. It's not like if you think of a spiral galaxy, that spiral galaxy is actually flat, right? It's all the stars are located literally in a disk. That's not, the universe is not flat. The galaxies are distributed in a completely three-dimensional sense. The space-time continuum is a 4D idea that we draw as a it's kind of as a fake 3D picture, right? But it's a 4D concept. It's X, Y, Z, and T. All right. So X, up, left and right, Y, up and down, Z, back and forth, and then time. And together, that is what 4 dimensions is about. And of course, that's very hard to draw or visualize. Okay. So the inflation of the universe flattened it to its overall geometry. Right? That's probably why we don't have a curvature. And that's another kind of benefit of the inflation theory, if you can call it a theory, maybe the acceptance of inflation, is that it explains a flat universe. All right? It's like filling up a balloon so much that if you're on that balloon, it appears flat to all the observers on it. Okay? Did inflation really occur though? Or is it just a stopgap in our understanding of the early universe? Well, temperature differences are greatest between patches that have a 1 degree variation, and that's temperature differences based on the cosmic microwave background radiation. Well, it turns out that that exactly matches the quantum mechanical mechanisms that would have been at play when the universe was very small and then suddenly expanded. And so the inflation definitely supports the variation in the cosmic microwave background radiation that we see. So we see those seeds left over in inflation. Okay? So, in summary, the overall geometry is flat, total mass plus energy has a critical density, ordinary matter is about 5% of that, total matter is 32% of the total, with dark matter being 27% of that 32%, which means we're only left to 5% for ordinary matter, right, as you can see. And then everything else that's not matter is dark energy. And by dark, we just mean mysterious. We don't know what it is, but there's some other energy source that's driving the expansion of the universe. And again, we'll talk about that more in the next chapter. And as I mentioned, the age a few times is 13.8 billion years. Okay? So, all of that is in an excellent agreement with observations of the present-day universe and models involving WIMPs. And WIMPs, by the way, are the proposed particles of dark matter, which are weakly interacting massive particles. So, what have we learned? A lot to take in here. The origins of the structure, the smoothness of the universe on a large scale, and the nearly critical density of the universe all are explained by inflation. The structure comes from inflating quantum ripples, so ripples at the submicroscopic scale, at the quantum scale. And then they became the structure of the universe now that is, hundreds of millions of light years across, or between those ripples. The observable universe became smooth before inflation when it was very tiny. And inflation flattened the curvature of space, bringing the expansion rate into balance with the overall density of mass and energy. Okay? So did it really occur? Well, we can compare the structures we see in the detailed observations of the microwave background with the predictions of the seeds, the quantum mechanical seeds that should have been planted by inflation, and so far, we see them. Okay? So there's nothing that's pointing it to being wrong, other than the fact that we don't have any physics to explain it. All right. So, observing the Big Bang for yourself. Why is the darkness of the night sky evidence of the Big Bang? It's kind of an interesting idea. Well, let's do a thought experiment. Okay? So in a large forest, a tree will block your view no matter where you look. Similarly, in an unchanging universe with an infinite number of stars, we would expect to see stars in every direction, making the sky bright even at night, because there should be an infinite number of stars, if the universe truly never ends. But we don't. Okay? We see that the universe is not infinite, it is not unchanging, and everywhere it's not the same. Okay? If we look further away, we see galaxies that appear to have different behavior, that they appear to be younger. When we look further away, we see galaxies that are moving away faster from us, and they appear to, again, be in a different generation of galaxies. And if we look far enough back, we don't see any more galaxies. So none of these criteria match. Okay? If that was the case, then stars would cover the night sky. They'd have to. There couldn't be gaps. But when we look with the best possible telescope, we see gaps. We truly do. And there's nothing to fill those gaps. There is not an infinite number of galaxies. There's a finite number of galaxies, about 100 billion, which is a big number, but finite. So the night sky is dark because the universe changes with time. As we look out in space, we can look back to a time when there were no stars and no galaxies. Okay? It's like being in a forest with a small number of trees. You can see the open space between the trees and beyond the trees. Okay? So the darkness of the night sky is evidence of the Big Bang, right? It's pretty indirect, but it's a nice way to maybe make yourself believe that at least there's a motivation for this theory, even if some of the details of the theory are a bit overwhelming. If the universe were eternal, unchanging, and everywhere the same, the entire night sky would be covered with stars, but it is not. The night sky is dark because we can see back to a time when there were no stars. All right. Well, thank you so much for watching or listening to this lecture talking about the Big Bangs and the origins of the universe. I hope it has been interesting and informative.